Well, good morning, everyone. My name is Péter Naszvadi, and I'm going to give a presentation about how mixed Hemming packing is involved for benchmarking QUBO solvers. This work is a joint work with my colleagues Mátyás Konyoltrik and Marcel Topora from Wigner Research and from ELTE. So, pinpointing Hemming packings can serve as a structured tunable bench. So it's so loud. Okay. Then, so QUBO solvers needs to be tested, and Hemming packings can serve as a very well structured and tunable, flexible benchmark tool for QUBO solvers, including covering both exact ones, GPU accelerated ones, and quantum errors. So, the usual outline consists of a quick roadmap, that motivation, one formal preliminaries, and also formal definition of Hemming packings, very brief introduction, and computational results that we made, and then conclusions, possible future directions. So, motivation. Why a new QUBO program class at all? We have 4 reasons. First, is very hard to solve, both in theory, both in practice. In a complexity sense, this means that it is still a $1 million problem. And second, and it's very small and common, only a few hundred qubits is still not enough to solve them efficiently. The third, it models a very relevant and important problem. I will show it later. Why is it important? And the fourth, that it is a benchmarking. Why is it important? It shows a totally different model according to the characteristics that we calculated. Now, the lingua franca of the easing computation is what is showed that both the easing problem, the QUBO problem, and according to the Maxwell problem, basically they are equivalent. It is widely known, otherwise not. Feel free to ask, and after the break. Hemming packings. After Richard Hemming, he introduced the Hemming packings in error correcting, and these are nothing but just Cartesian products of finite sets. These double Z marks are not related to the underlying algebraic structure. They are just the bottom right index denotes the cardinality of the set. The set's elements are called code words. Now, Hemming distance. In order to get a metric space, we introduce a metric, which is nothing but comparing 2 code words and summing, adding all the different positions as well. And any non-empty subset of the Hemming space is called Hemming packing for a given D, a given positive D, if any different tuple in it has a minimal Hemming distance, at least D. So now we are going to address our key question to optimize. Oh, pardon, no room error. So we are about to optimize. Pardon, we are about to optimize the cardinality of every non-empty subset of this, and this is the formal description of this model, this scalar quantity. And what is good to know that any Hemming packing problem can be formulated as a packing mixed integer programming problem. And what's more, without the loss of generality, any QUBO with non-positive diagonals, above diagonals, non-zero elements are all positive and is being dominated by corresponding diagonal values. And this matrix is basically an underlying graph's adjacency matrix scaled well for our purpose. And the Hemming packing problem can be transformed as MIS. Sorry for the confusing 3-letter acronyms. They are just a Hemming distance, exactly 1 from MIP. Why is it important for us? for gamblers, football poll systems, betting systems, drug screening, DNA sequencing, data compression, telecommunication protocols, error correcting codes, mandatory 5 seconds break to get attention, and quality assurance, I mean orthogonal arrays, orthogonal packing arrays, engineering. So this is the dummy binary programming model to determine an AHD. The objective function is the argument of the max. This is about the minimized. The variables are the x indexed with the code words, and these are truth variables. You can have values 1 or 0. And such truth variable is 0 if and only if it is selected to the code, the packing. Our subject to that, the constraints are mutex constraints, and these are excludes two code words to be selected if they are too near each other within d-1 Hamming distance. So it is also known and recognized that this kind of algebraic structure of the linear programming matrix is a maximum independent set problem if the type of the variables are all binaries. And the spoiler, in the corresponding QUBO model, instead of the constraints, we are about to penalize the product of two truth variables that corresponds to two code words that are near each other. So this is a binary programming model on steroids. We extended with the bottom line. These type of constraints came from the Thomas problem. And this is our contribution to the combinatorics side. This paper came out last year to prove correctness of these constraints. And what's more, the key result, we ensure in this special particular case that at least one optimal solution will be kept in the feasibility region. Now a bare and dummy QUBO model. The matrix is a parameter, and we are able to optimize this. And this sign is because we have sensitive packing, and it's due to the sense of the objective function, the minimization, it needs to be converted because the energy level, the objective function cost will be negative. What we added. Again, our results cover that the penalty weights can be 2 or even 1 because of the fixed point arithmetics that are used commonly in annealers or unsimulated annealers. And for physicists, another not yet published results just on quantum devices is a very important thing that every subpacking is feasible, and this provides a weird and a unique property that every energy levels are equidistant that can be set with particular spin configurations from the optima to 0. And we also know the step, but we don't know the optima, so that's that it still remains challenging and NP-hard. Now, pardon. So now, this benchmarks and solvers. SCIP for Etalon purpose. These are not QUBO based. These are mixed integer linear programming solvers. And we use to determine all the objective values, including dual ones, and proving the optimality of our models up to 1000 qubits or integer variables after pruning. Eurobi is used as an exact QUBO solver. This is the other engine that could provide dual witnesses to prove the correctness of the model solutions. MQLib is a collection of heuristics, very comprehensive and covers all state-of-art tabu search, whatever QUBO max-cut heuristics that we could use in real life. And also, we tried out, made a test drive with a simulated bifurcation engine, the QuantumZ.io. And we got some credits in order to try out D-Wave again. A selected number, very few models also can be run because it was so expensive. But it was informative what we've got. So let's compare fast the two solvers that could provide formal witnesses to the correctness of the solutions. MILP, this was the fastest among providing the dual witnesses compared to the exact QUBO solver, which found this problem too tough. Despite the Eurobid, the exact QUBO solver found the primal solutions, the real ones that we use in real life. It was very hard to prove them, and sometimes it was unsuccessful due to the cycling and the numerical instability. MQLib. It's a primal heuristic collection developed to solve and implement and solve these heuristics up to 27. Am I right? Yes, 27 total. And there were at least 150 models, but they are reduced because of the decomposing and pruning. Pardon. So let's say something about the results that provided with by the MQLib. This table shows the most difficult problems that caused headache for the MQLib, especially the instance which can be solved formally, the bottom one. This can be proved formally using only some algebraic methods outside of the paper. And 12 of the 27 algorithms goes to failing to find the primal optima on this. SBM, our absolute winner on the primal side. SBM found all but in 7 cases the optima in a snap less than 0.3 seconds. According to my little software ergonomic knowledge, this means that all solutions could have been found in a snap. And what's more, the solution quality of the unsuccessful runnings is also good because the MIP gap is at most 2. Like this. For the curious one, the simulated bifurcation machine parameters were 1096 samples, 4K steps, and the DT was 0.05 D-Wave. We were able to run only just 3 models on D-Wave, and there is a not too brief summary. I have to detail. So the 2 smaller model that we choose on some further several considerations can be embedded in some parametering, but the biggest one, which also have a so-called singleton sharp solution, is failed to be embedded in all configurations. It's in the bottom line. Despite so many failing, this was so informative. Why? Because all models trigger chain breaks, both repairable and unrepairable. The latter one unfortunately caused stopping the solving process. And now we tried out almost 800 de facto standard instances bundled with ours, and then made a comparison on the following slides. These slides are de facto standards for testing QUBO's max cuts and using instances as well. The famous G set from Vigele and Guzmeroli and Rinaldi, the QPLib, the type planting, two-dimensional and three-dimensional QUBO instances, and last but not least, the IBM Heavy Hex, a very large collection of QUBO reformulations with relatively small penalty values. Now, what about the classification of our model? We made a PCA projection collecting 58 properties that are being tested and developed on the MQLib. The MQLib is open source, and it has an interesting capability that there is a switch of which you can force that shows that performs some trial and error result and testings on the input QUBO models and then classify them on a paper. It's published by the MQLib authors. And these classifications contains that 58 parameters on which the models are classified. And there are uncovered maps in these classifications, and our QUBO instances, after converted to MaxCut, covers some holes like these. These are our contribution, the Hamming balls, denoted as balls, hence the name, here and here. And together with these two-dimensional, four-dimensional to two-dimensional projection, the intersection pinpointed that the QUBO region is unique and cover a big hole. So it provides a new family of testing models. So two confirmed, partially confirmed conclusion is upcoming. D-wave, long chains and chain breaks. Expect the expected with these very symmetric models might and do or did cause chain breaks and failure to even the embeddings, the so-called presolving process of the D-wave annular. These are dense matrices and dense graphs. Continuous methods unaffected by a flat landscape. A flat landscape is where usual mountain climbing heuristics cannot get through. So they are trapped in it. And SBM did the best in solving the primers. More than 95% of the instances had been done, and the remaining ones also got a particularly good quality solutions. Partially confirmed results include that discrete local surge, also it can be trapped, and the MQLib showed these ones, and we can also pinpoint it that the weakest algorithms can be omitted in the future for further considerations. The remaining 9.1 is about to used and proposed for the QUBO interested audience. Small maximally independent set. It's a graph theoretic optimization problem. Coordinated moves needed due to the symmetry breaks again, but not the symmetry breaks and the D-wave. And the quantum processing unit is about both the simulated bifurcation one and on the quantum, the QPO gap grows within asymptotically. It's conjectured it's to be linear or quadratic, not the speed, but the size. The conclusion. MQLib beats MILP in primal solutions as well as QUROBI and SBM. MQLib and MILP primal solutions show positive correlation, but the biggest correlation in time to find the primal solution. The dual prover QUBO solvers shows relatively poor results. The QUBO engines included in the QUROBI. SBM was a primary ultimate winner. And about the model classification, a new benchmark model class with unique properties is provided and published partially in our paper last year. There is a bundled online resource that is updated regularly and maintained by me and my colleagues. So, and briefly, that's all I wanted to. And thanks for the patience. And now questions are always welcome.
Thank you very much, Peter. So, time for questions.
I just want to ask, you said something, the numbers in the QUBO were positive?
Pardon?
The numbers in the QUBO are all positive? Is that right?
The coefficients in the
Yeah, the
QUBO,
coefficients.
except the diagonals.
Oh, okay. Because I'm also wondering the range of values of your coefficients, because when I was experimenting with D-Wave, I found that it wasn't just the chain breaks, but also how your coefficients scaled. And do you have a problem, or do you have a solution to the problem if the coefficient range is too broad for maybe making a bigger QUBO with smaller coefficients to map to hardware?
Are just speculations. We only tried. I just remarks I cannot answer this question as well. Our experience was that we believe that it's more depends on the structure of the QUBO instead of the values, because D-Wave still struggles on that. Only a small range of values can be used because of the very specific finite precision arithmetic.